Check it out now, y'all.
NanoHub U, online instruction.
If you remember in the last lecture, we derived a number of important formulas to describe wave vectors and energies for electron states in the free electron model. We use sodium as a prototypical element to evaluate some of these formulas, and we were able to come up with important parameters that describe the free electron gas in a sodium metal. So by way of review, possibly the most important formula we derived was the formula for the Fermi energy, right? Fermi energy is the maximum energy that's filled by electron states, and it's given by some fundamental constants times the ratio of the number of electrons per unit volume raised to the 2/3 power. And this quantity in parentheses is often abbreviated as the Fermi wave vector K sub f, and that then allows us to write the Fermi energy in terms of our familiar h bar squared k squared over 2m formula. The picture that is associated with this formula is a free electron parabola, which indicates the energy versus k vector. The first reciprocal lattice vectors are indicated on this axis. It's 2 pi over a and minus 2 pi over a. Well, the plot is for kx, but it could as well be for ky or kz because this is now a three-dimensional problem. And the basic idea is all the states from E equals 0 up to this Fermi energy E sub f, those are all filled, and all the available states above E sub f are empty, right? So they're not filled because there's not enough electrons provided by the sodium atoms to fill up these energy states above E sub f. We also evaluated K sub f for the parameters appropriate for sodium, and we found that K sub f was about 60% of this reciprocal lattice vector 2 pi over a, where a is, of course, the separation between atoms in a sodium metal. So this is the important picture that you should have from the previous lecture. There are many ways to visualize these results, and I'd just like to real quick show you a few. Right, if you start to plot E versus, let's say, kx or ky, right, actually for any direction of k, you're going to have a parabolic E versus k curve. All the states up to this Fermi level are going to be filled, so I've indicated that by this shaded orange line. All the states above E sub f are unfilled. Another way to visualize these results is to plot the filled and unfilled states as a function of kx, ky, and kz. So for a free electron metal, kx, ky, and kz are all equivalent. All the electron states are filled up to a value of k sub f, and this value of k sub f is isotropic. It does not depend on which orientation you're moving through in k space. You've got the same value of k sub f. So you end up with all the electron states filled inside this sphere, which is referred to as the Fermi surface. All the states outside that sphere are unfilled, and those are states that are above the Fermi energy. These results apply for T equals 0 Kelvin, and at T equals 0 Kelvin, there's a very sharp boundary between the filled and the unfilled states. Okay, so that's the picture that emerges from our discussion from last lecture. In this lecture, we're trying to extend those results. We want to include finite temperature, see what new effects come in, and we also want to discuss the density of electron states in the free electron model. That turns out to be an important parameter that's required for this discussion. So let me just briefly remind you what we did previously. We counted the number of states that were filled, and we did that by saying we have a factor of 2 for spin degeneracy, and we multiply that factor of 2 times the number of occupied states, and that then tells us the number of electrons that are present. The occupied states were characterized by this value for capital M. This value for capital M contained the quantum numbers mx, my, and mz for these electron states in the x, y, and z direction. And what we were able to do was we were able to find an explicit relationship between the quantum number capital M and the energy E. And the relationship between the quantum number and the energy is a square root of E value. Right? So this is a rather complicated argument that we went through. It turns out there's a much simpler way to get the same answer, and I'd like to describe that to you now because you'll see this simpler approach in many different textbooks. If you get confused, you can always go back and think it through, but this way is the second way of counting the number of electrons in a metal is what you'll find in many textbooks. It relies on this idea that there's a fine-grained structure for the electron states. So these values of k, let's say k sub x, it could be just as well ky or kz. These values of k sub x are separated one from another by 2 pi over L, where L is the dimension of the crystal in the x direction. And so what we can say is we can say that each quantum state in one dimension occupies a distance of 2 pi over L in the kx direction. If you extend this argument to 3 dimensions, where you're going to have a kx, a ky, and a kz, then this minimum distance for each k value now becomes a volume in 3-dimensional space. So basically each allowed state requires a volume of 2 pi over L quantity cubed, where L again is the dimension of the crystal. So it's convenient to assume that the dimensions of the crystal in the x, y, and z direction are all the same. So that's how you just get one value of L in this expression. So once you realize that, then and if you appreciate the idea that all the states that are filled at t equals 0 are contained inside of a sphere of radius k sub f, right? Once you realize those two facts, then you can calculate the available states at some arbitrary energy E as a function of the k vector of that particular energy state. And the way you do that calculation is you take a factor of 2 to include all the spins. You take the volume of all the k states that are filled inside a sphere specified by some wave vector k. So the volume of the sphere is just 4 pi 3 over k cubed, right? And then you divide that by this quantity 2 pi over L quantity cubed. That's the volume that each k state takes up. And when you work through all that arithmetic and you include an expression for energy, what you find is you find an exact expression that matches the case where we counted the individual states in terms of the quantum numbers mx, my, and mz. So this formula here matches exactly what we got in the previous lecture, and it just basically tells you how many available states there are as a function of energy E for an electron of mass m sub e in a crystal which has dimensions L cubed. It's very often in some textbooks you'll find that these number of available states is divided by the volume of the crystal L cubed, and so then you find an equivalent expression for the density of, for the number of available states at energy E in terms of states per cubic meter, right? So these two expressions are equivalent. It's just that in the bottom expression we've divided out the volume of the crystal that we're considering. And in particular, if you apply these formulas to states at the Fermi energy, then you're basically going to substitute K for K sub F, and you're going to go through this evaluation again. You're going to find a number of electron states at the Fermi energy. Now it's going to be given in terms of the Fermi energy E sub F instead of an arbitrary energy E. So this derivation here, right, is so simple that possibly you won't forget it. Where if you go through and try to follow through the derivation that we gave in the previous lecture, you have to take into account a lot of the details, but you get the same answer either way is the bottom line. It's important at this point to kind of summarize what we're kind of interested in when we're talking about electron states and solids. And I like to make the case that we're really interested in four quantities ultimately. When all the dust settles, there's four things that you usually like to know. One thing you like to know is you like to know where the position of the electron is in the solid. And if you know the wave function, then you can evaluate the position by just taking the wave function times its complex conjugate and multiplying by a volume element d sub v. So if you tell me the position r and you evaluate the wave function at that position r, then I can tell you what the probability is that you're going to find that electron at that position. Once you know the position, the probability density that describes the position of the electron in the solid, it's often useful to ask where the charge is located. And the charge is going to be located just simply by multiplying the position by the charge on an electron minus E, right? So this will tell you the distribution of charge in the solid. It's also very useful to know what the energy is for a particular K value. So in the case of solids, this K is basically telling you the quantum numbers that we derived, for instance, when we discussed the hydrogen atom. Remember, for the hydrogen atom, we had four quantum numbers. When you consider electron states in solids, the quantum number is essentially this value K, because this is going to tell you the allowed values of K for the electron state in that solid. So it's useful to know this energy, E of K. And then lastly, it's useful to know the distribution of these states as a function of energy. And that's this concept of density of states that we've talked about many times throughout the course. And so now what we like to do is we like to actually calculate the free electron density of states from what we've already derived. And that discussion is pretty simple, because the first thing we need to do is we need to calculate the total number of electrons as a function of energy. Using our very simple argument that we've just outlined, we've got a general expression for the number of electrons as a function of energy E. We can then take the derivative of that with respect to energy. When we take the derivative, the e to the 3/2 becomes an e to the square root dependence. And then we can identify the relationship between the number of electrons at energy E and an energy interval delta E, right? The proportionality constant between these two quantities is just our density of states, G of E. And by just direct examination, we now have an explicit expression for the density of states for free electrons in a three-dimensional metal, right? And this functional dependence of G is a square root of E functional dependence. So that's an important result. We should probably evaluate G of E at the Fermi energy for a 1 cubic centimeter piece of sodium. So that's what I worked through in this equation, right? The I pick E sub F for sodium metal, and I'm going to just evaluate this expression for the density of states. I will say that up front, this quantity G of E is represented by different symbols in different textbooks. Sometimes this is given the symbol capital D of E. Sometimes the symbol rho of E is used. So depending on which textbook you read, you maybe have to transform my notation, which I use G, for some of these other values. But here I actually I go through the calculation. I use the dimension of the metal to be 1 centimeter. That's 0.01 meters. I need to know the mass of the electron. That's 9.1 times 10 to the minus 31 kilograms. I got to know what H bar is. I've got to know what the Fermi energy is, right? I have to take the Fermi energy to the square root power. Fermi energy has to be given in joules, so I have to convert my 3.09 electron volts into joules. And when I work through that, I find that I've got about 7.5 times 10 to the 40 states per joule of energy at the Fermi energy in a 1 cubic centimeter piece of sodium. So there's a huge number of electron states per joule. But of course, the unit of energy for joule is extraordinarily large. It's not appropriate for discussion of electron states. It's often more convenient to convert joules into electron volts. And when you do that conversion, then you find there's something on the order of 10 to the 22 states per cubic centimeter at the Fermi energy for electrons to exist in sodium. So these huge number of states, right, tells you something about the nature of electron states in solids compared to, let's say, electron states in an individual atom, where the density of states is considerably less than this. And this huge number of available states, right, is just a reflection of the fact that there's a very large number of sodium atoms that make up a 1 cubic centimeter piece of sodium. So you shouldn't be puzzled by the value of the density of states at the Fermi energy. You should just be able to appreciate what it's trying to tell you, that there's a large number of states available. The next logical topic is how many of those states are actually occupied, and to do that calculation, we have to refer you back to a previous lecture where we, after a lot of work, we finally came to the result that the number of occupied states as a function of temperature was equal to the product of the density of states as a function of energy. So this G of E is a function that depends on the individual system that you're considering. Each system is going to have a different expression for G of E. You've got to multiply G of E by the probability that a particular state is occupied at a temperature T, and then you've got to multiply that by the energy interval that you're interested in. That's the dE. So G of E we've got from the previous slide. That can be written in a number of different ways. It's the square root of E dependence. So here we're evaluating the density of states at the Fermi energy because our energy E is equal to E sub F. To calculate the number of states that are actually occupied at the Fermi energy, right, or at an energy E, it doesn't have to be the Fermi energy. The number of states that are occupied at energy E as a function of temperature T is taking the density of states function and then multiplying it by the Fermi-Dirac distribution function that includes the statistics, the Fermi-Dirac statistics that are appropriate for electrons. So this derivation includes the factor 2 for spin because that was put into the calculation up front. If the spin is not included when you calculate the density of states, then very often you'll see a factor 2 in the numerator of this Fermi-Dirac distribution function. So it's just a question of where in the calculation you account for the spin of the electron. But this is then the result. This tells you, this is a very important result. It tells you the number of electrons is a function of energy that are occupied as the temperature T of the metal is changed. We can make some plots to make the formulas a little bit more easy to understand. So what I do here is I show the density of states in red, and the density of states has this e to the 1/2 functional dependence associated with it. I must multiply that G of E curve by a Fermi-Dirac distribution function, and I list a few different shapes for the Fermi-Dirac distribution function. At T equals 0, at 0 Kelvin, the Fermi-Dirac distribution function is unity all the way up until E is equal to E sub F. Then it drops abruptly to 0. And this gives rise to this very sharp demarcation between filled and unfilled states that we discussed at the beginning of the lecture. All that discussion was for T equal to 0. As you start to heat the metal up, right, the Fermi-Dirac distribution function starts to deviate from unity. The deviation from unity occurs at energies a few kT around the Fermi energy E sub F. And so this curve is then, the Fermi-Dirac distribution curve is then broadened, as I've shown by the dashed line here. It's important to realize that independent of temperature, right, the Fermi factor is equal to 1/2 whenever the energy E is equal to E sub F. That's pretty easy to see because when E is equal to E sub F, the argument of the exponent is 0, and that means E raised to the 0 power is 1, and 1 plus 1 is 2, so the Fermi-Dirac distribution function is always equal to 1/2 when the energy E is equal to the Fermi energy, right? So the net result for the number of occupied states as a function of temperature is indicated schematically in this bottom curve. For very small energies, for energies much, much less than the Fermi energy E sub F, the number of occupied states rises as the square root of the energy E. And then as you start to get close to the Fermi energy, you find this characteristic rounding of the number of occupied states due to the Fermi-Dirac distribution function. So this is referred to as a thermal smearing, and it actually shows that you've got electrons above the Fermi energy at finite temperatures, and the smearing of this region between occupied and unoccupied states, right? That smearing is on the order of K Boltzmann times the temperature T of the system. So at very low temperatures, this is a very, very narrow range, and as the temperature gets higher and higher, right, the range of thermal smearing increases. So that's the answer, right? That's the answer for the number of occupied states for the free electrons in the metal. So that's the important result for this particular lecture. We've only got a few more topics to cover in our discussion of electron states and solids. The next lecture, we're going to discuss very briefly the nearly free electron model. This is an attempt to relax the rather unrealistic constraints of the free electron model that we've discussed for the previous two lectures. And when we put in a periodicity associated in the electrostatic potential energy, and that periodicity is going to be associated with the lattice constant A, we're going to see that some really new and interesting effects arise, and these new effects provide the explanation for why some elements are insulators, why some elements are semiconductors, and why other elements are metals. So that's going to be the next topic, and hope you'll have a chance to listen to it, because some of the results are rather surprising, unexpected, and very important to understand. And if you want to appreciate the difference between different types of elements in the periodic table when they condense to form solids. So we'll see you when that lecture starts.